Hello everyone, my name is Gokul. Today in this video we are going to see about how to solve word ladder. So let's see the problem statement, the approach, how do we solve this problem and code for the solution. Okay, so if you're clear with the problem statement, you're free to skip. Yeah, let's proceed. So we are given a word, begin word and end word. So we have to travel from begin word and we have to reach the end word by transforming the begin word to another word by changing just one character. Okay, and also we are given a list of the word that we have to transform to. Okay, so hit, if you change one character, that result word should be available in the list, in the word list, and you can pick that up and you move ahead with that word, and then you change one more character, you move ahead, and you do this until you reach the end word. Okay, so let's see with an example. We just want to change one letter here. So the difference between these two words is just one character difference, right? So we can easily transform from hit to hot. So we can just transform to any word, like change the H to the next characters, HI or G or anything, but that should be available within this list. So we have to pick a word which is available in this list. So if we change this word, the only possible option is hot. Okay, so we change from hit to hot, and then we have to change from hot to either dot or dot. Okay, so which we can change this H to L or D. Again, if we select this D dot, so we are moving ahead and picking this word, dog, and then finally we are reaching our end word. Okay, so if you see along this word list, just one character difference you can see, and we are reaching the end word by constructing a sequence. So we are forming a ladder kind of, okay, hit, jump to hot, jump to dot, jump to dog, and finally reach the end word. So this is one solution which contains 5 words. Okay. So likewise, we have multiple solutions. If, for example, if we move this path, okay, so we'll have the log word and directly. So this solution also uh, consists of 5. So likewise, there are many solutions. So log can go to dog and then again cog, which leads to the 6, which is we are not interested in longer distance. So likewise, so there are other solutions like this. Uh, log can go to dog. Yeah, dog again go to cog. Okay, so just so among all these solutions, we have to pick up the minimum length. Okay, so we have to pick up the minimum length and then just return this. So how soon you can reach the end word? Okay, so by traversing the minimum set of words, you have to reach the end word. Okay, so clear? Um, you can see we have several list of conditions here. So I have just rewrote here. We have to return 0 if there is no such sequence. Means there is no end word in the list. Okay, so we cannot reach, right? We will not be able to reach the end word if the word list does not contain the end word. So in that case, just return 0. Next, all words have same length and lowercase alphabets. That's fine. And no duplicates given. Yeah, which is very good. So begin word and end word will not be the same. Of course, right? So begin word, if it is equal to end word, you will not touch the word list. You'll just say problem solved, just one word. I've already reached the end word. So that is not the case here. We have to, at least given list of test cases will always have a solution. Okay. All right. So what is the approach? I hope you are familiar with BFS. So we have to travel if we are at node A, so we have to consider all our children first, okay? And then after reaching this node, child 1, we have to explore all its children and have it in our list. So basically BFS is used to solve this problem. For this instance, we start from hit and move to hot and lot, log, and cog. So this is one solution available for our problem, right? So, and similarly, this is another solution, which is of 5 nodes, and this is of 5 nodes. You can also travel from hit, hot, lot, and log, dog, and cog. So there is no limit. So you can just travel from anywhere to anywhere. But we have to keep our number of words that in our sequence very minimally. So we have to try reach the end node as soon as possible. So yeah, let's start to code this. Okay, so hope the problem statement is clear for you. Yeah, so I'll remove this for the space. In order to perform BFS, we'll have to consider all the children first, as I already mentioned, into the processing list. Okay, so we have to have a processing list. Okay, so let p list, for example. Okay, it's an array. For the processing list, we will be starting with, for example, one operating node, let's say one, and its children. So we are exploring its children. So we are actually appending all its children in the processing list, like 1.1, 1.2, 1.3. Okay, so which means one has three children, and we are actually taking the whole list and appending to the processing list. So after we are done with one, so we'll pull this out and we'll start processing 1.1. So so we eventually touch this 1.1 and its children, after completing all one's child. Okay, so which means so pick up this 1.1 and append all its children, right? So and pop this out, and if you're if you're touching this, then you'll append all its children. So basically what you're doing, you're processing the node and its children one by one and exploring all their children, so like grandchildren, and just appending to your processing list. Okay, so this by this you can actually perform breadth first exploration. All right, so hope it's clear. So we are going to do the same way to solve this problem. So let's have a queue, okay? Because the processing list looks like more or less a queue, right? So let's have a queue, and the queue initially has the begin word because we are going to, jump from this word. So begin word and the length of number of words. It's just one, right? So we start from this, and while uh, it's while the queue is not empty, then we are just popping out that. Okay, so word and the length. Okay, so q dot shift. So we have this function in JavaScript. So shift means it will just remove the element from the beginning of an array, and there is one more method called pop. So it will just remove from the last. So just remove one element from the end of the array. So we are going to use shift because we're going to process the first element. And then let's check this word, whether I can transform this word into any of the available word in this word list. Okay. So if any word is available in the word list, I have to, perform the operation with that word. Means I have to pick that word and add it to our processing list, which means the queue. Okay, rather than looping through the entire list for the adjacent word. For example, if I got hit, I'll be comparing with hot. Okay, like hot. So I'll be comparing character by character with hot. So whether it is equal, and the difference between these two string is one or not. If it is one, then yes, this is the adjacent word. And again, I'll move to another, uh, another word and check what is the difference. So, which means I'll take the current word and I'll compare with, each and every word in the word list. So that'll take huge time because uh, if the word list is very huge, then for each and every word, you will have to scan the entire list, whether this is adjacent or this is adjacent or that. So in the condition, based on the condition which is given here, we can just change each and every character from A to Z and check whether the word list has that word or not. Again, if you generate, for example, if you generate hit. For example, I am exchanging the first character, AIT, which is, you know, I am changing H to A, which is very adjacent, AIT, right? This is the word I have generated by changing just one character. Uh, this AIT, I have to quickly look whether this word list contains this word or not. Again, I have to scan, right? So we have to take this element and check one by one whether this is equal to the first element or second element. That will be again a costly operation. So I have to have a quick lookup. So I don't want to spend the entire time on scanning each and every item in the word list. Rather than if I say this word, whether it is available, just the constant time it has to return true or false, right? So what is the best data structure used for it is hash table, right? So we have to have, key value based. If the key is available, yes, true. It's O of one of time complexity. So let's, add every word to the hash table. So I'm creating a table, which is an empty table right now. And for each and every word, okay, so I'm having a word, just table of that word, make that as true. So I'm putting that entry. By this way, I'm creating keys for all the words. So I can just check in a constant time, table dot has own property of word. It returns true or false. Okay. So this is the operation I'm going to do. This is the way I will achieve the lookup, the faster lookup. Okay, so how to generate a new word out of the existing word? So let's loop in through each and every character. For example, let I, so I have to loop through the length. So word dot length plus plus, and let new word or the adjacent word equal to word. I have to, there is no implicit API available to replace one particular character in JavaScript. So I'm going to, slice from 0 to that particular index plus my new character, which will be available now, and word dot slice again from the index plus 1. So I have to fill this character, right? So for let character in A, B, C, D, E, F, G, H, I, J, K, all the characters. Okay, so this condition is very useful for us now. So all the lower contain only lowercase alphabetic characters. So I'll take this and replace this with C. Okay, we'll get a new adjacent word. So I have to just look that up. Okay, if the table that has own property of adjacent word, okay, which means that we can transform to this word, then add it to our processing list. So q dot push, add this word and increment length because we are adding one more word to the chain, right? So after pushing this, I should not relook that because this word has been already taken. So we should not, Again, the word should not be retaken by some other chain. So to avoid that, we will remove this, okay, from the word list. Table, or just say delete that key, delete table of adjacent word, okay? So we just remove that key, that entry itself. All right. So before pushing it, what we can do is, so this is a word which is very adjacent. Okay, we are going to process this. But if the reached word, if we are, finding a word which is transformed, what if that is the end word, right? So if that adjust word, if it is end word, just return length plus one because we have reached the end word that also should be included in the length. So we just returned it. So we got the answer. If not, if that is not the end word, we have to still process. So add it to the processing list. Okay. So if the queue is empty, so we are just uh, transforming and transforming, and there are no other words to transform, and we didn't get the end word either. So in that case, just return 0. All right? Okay, so I think everything is good. We can test this out. Yes, it works. All right, so let's go ahead and submit this. Yes, it works. So we are faster than 68% only. Uh, okay, because we're not 100%. Why? There is another solution which has, which runs in very less time. That is called bidirectional breadth first search, right? So you start from start and you uh, uh, trace from start to reach the end, and you consider the end word also as start node, and you will start tracing parallelly. So eventually you'll hit in the middle. So the overall runtime will be reduced to just half. You know, you will not travel the whole sequence. Rather, you'll hit the in the middle itself. So that will be even more efficient than this solution. Okay. Hope you enjoyed this video. If you have any queries, do let me know. And thank you very much for watching.